Hello friends, in the previous video I have explained you how to draw the pressure distribution diagram in a cantilever sheet pile penetrating clay bed. Today we will take one example so that you are conceptually clear and the application is also clear to all of you. So the example looks like this. There is a cantilever sheet pile. This is the cantilever sheet pile, which is penetrating a bed which is clay in nature. So the value of phi is going to be 0, and the value of undrained cohesion is known to us 50 kilopascal. And the unit weight is gamma 1 uh, on both these sides. So this is the cantilever sheet pile. The sheet pile is penetrating this clay bed, and the backfill here is going to be granular or phi backfill, phi soil. The unit weight gamma is known to us. The unit weight is 20 kilonewton per cubic meter, and it is in dry condition. And the value of phi, angle of internal friction, is 30 degree, and the height of this cantilever sheet pile is 3 meter. We need to find out the depth of embedment. So for this sheet pile, find the depth of embedment. Capital D. So it is embedded in the cohesive bed. So this is the sea soil. And the depth of embedment is D. H is already known to you. And you know the pressure distribution diagram for phi soil, it is going to be linear over here. And you can find out the magnitude of this. So what is the active earth pressure at h equal to 3 meter? That you can find it out. So here, first thing, we will be finding out the depth of embedment. Second thing, we will try to find out the maximum bending moment across the height of the cantilever sheet pile. So this is the cantilever sheet pile penetrating cohesive bed. So the pressure distribution, here it is going to be active, and you know the magnitude, if I call this point as A, the bottommost point as B, and this point at the dredge line as D, so the at h equal to 3 meter, the lateral earth pressure, which is going to be active, can be found out. So PA equal to K into gamma into H, and K for phi equal to 30 degree, the value of K will be 1 by 3. So it becomes 1 by 3 into 20 into 3. So this 3 goes out. This becomes 20 kilopascal. So this pressure is going to be 20 kilopascal. Now, the pressure here at this location is known to you. You know the pressure at this location is going to be like this. It will go like this, and finally it will go like this. And this pressure this unit is going to be 4C plus gamma into H, where there is going to be gamma into H. For phi equal to 0, the value of K for cohesive soil and Kp both will be equal to 1, because the value of phi is 0. And the value here will be 4C minus gamma H. So you know the pressure distribution diagram, and therefore from the pressure distribution diagram you can find out the magnitude of this one here. So the value of C is 50. Therefore, on the left hand side at D, you can calculate the magnitude of D. Say this is D1. So DD1, this pressure is going to be passive in nature, and this pressure is going to be, the net pressure is going to be 4C minus gamma H. So calculate this pressure, 4C minus gamma H equal to 4 into 50 minus this side, this is gamma is already known to us, and it is given as 20 multiplied by 3. So gamma H value is going to be 60. Gamma into H becomes 60. So this becomes equal to 200 minus 60, that is 140. So this value of this is going to be 140 kilopascal. And the pressure here at the bottom, that is at B, the pressure can be found out, and this pressure is going to be 4C plus gamma H. So this also you can find it out. So 4 multiplied by 50 plus 60. So this becomes 260 kilopascal. So this value is also known to you as 260 kilopascal. This becomes the pressure distribution diagram, and this is called the depth of embedment. Now, say this distance up to here is going to be Z. So if I take this distance as, let's say, from the bottommost point, this distance is Z. Then you know that from the condition of equilibrium, the algebraic sum of all the horizontal forces must be equal to 0. So this gives you the value. You can find out the area of this pressure distribution diagram, and that gives you the total active earth pressure. This becomes PA. So you can find out PA first, and PA will be the area of this diagram, that is half multiplied by base multiplied by height. That's the area, triangular variation. So this becomes equal to 30 kilonewton per meter length of the wall. So this magnitude is known to you, 30. And let's say the point of application of this PA from the dredge line is Z bar. So you can find out the value of Z bar, which will be 1/3 of 3 meter, that is equal to 1 meter. So Z bar from the dredge line is going to be 1 meter. So friends, the magnitude. Now, if I say that PA is acting this way, then if I apply this condition, equilibrium condition, then PA minus, this is acting this way, the area of this rectangle, complete rectangle, this DD1, B1B, this whole area, you can find it out as 140 multiplied by D. So the area is going to be 140 D. And this is going to act like this, hence negative. Now this is going to act like this. This area in excess we have taken, deducted, because we have taken the complete this, and therefore while taking complete triangle from here can be taken. If I call this point as E, B1, B2 can be the total area. So total area of E, B1, B2 must be equal to 0. So sigma Fs equal to 0, or the magnitude of PA is already known to me So 30 minus 140D plus the area here is going to be 260, this plus this is going to be 140. So complete base, this triangle, the half. So this plus this, 1 by 2, this plus this, into this distance has been taken as z. So you multiply it by z. Must be equal to 0. So friend, you see this, that sigma fh equal to 0 yields the value, and we can find it out. So sigma fh equal to 0 gives me the value like this. Therefore, I can find out this value which is unknown, the value of z. So value of z can be found out from this one in terms of d. So 260 plus 140 becomes 400, divided by 2 becomes 200. So I can write it, or 30 minus 140D plus 200Z equal to 0. Therefore, Z equal to 140D minus 30 divided by 200. So the value of Z can be easily found out. 140D minus 30 divided by 200. So this Z you have found out in terms of D, and D is unknown, which you want to find it out. Now sigma fh equal to 0 has given you the value of this Z. Now if you take the algebraic sum of moment about this B, and it must be equal to 0. And therefore, by taking the moment, I am going to have PA multiplied by D plus Z bar will create a anti-clockwise moment. So this PA into D plus Z bar, and then this force, you can find it out. This force, this force was already known to you as 140D. So minus 140D about B, the force will be acting at D by 2. So it becomes D squared by 2. So this force has been taken into consideration. Now, if I take the magnitude of this force, this is going to be creating a anti-clockwise moment. This was creating a clockwise moment. This will create a anti-clockwise moment. So plus. Now, what is that force? It was that force was 200 Z. So the force is 200 Z, and from B it will be acting at Z by 3 must be equal to 0. So PA is already known to me as 30 kilonewton into D Z bar is already known to me as 1 minus 140 by 2 becomes 70 d square plus 200 divided by 3 into Z square. Now Z is already here. From 1 you can substitute it as 14d minus 3 divided by 20 whole square. This can be simplified and written as 14d minus 3 divided by 20. 0 can be curtailed out. So this must be equal to 0. So I am going to get an equation of this nature where only unknown is d. So if I take out or if I further simplify it, 30 d plus 1 minus 70 d square plus 200 divided by 3 into 20 square into 14 d minus 3 whole square equal to 0. So for the simplification, we'll see that if you simplify it further, this becomes 400. So 200, this becomes 2. So this becomes 2. And 3 2 ja 6. So further simplification, we'll see that or we can write it that 30d plus 30 minus 70 d square plus 3 2 ja 6 into 14d whole square must be equal to 0. A square plus b square minus 2ab or 30 d plus 30 minus 70 d square plus, let us simplify this one. So 196, so minus 70 d square plus 1 upon 6 into 196 d square plus 9 minus 84 d equal to 0, or 180 d plus 180 420 d square plus 196 d square plus 9 minus 84d equal to 0. So we can take this together, d square value. So this becomes equal to minus 224 d square. So minus 224 d square. Now here it is 180. So take it 180 minus 84 equal to 96. So this becomes plus 96d. So this and this is over. Now this is 180 plus 9. So finally this one and this one. So plus 189 equal to 0. Or we can write it that 224 d square minus 96 d minus 189 equal to 0. Therefore, we can find out the value of d very easily. So let us find it out, the value of d. So it is a quadratic equation. You can solve it, and you can therefore find out the value of d. Or you can directly find out the root, d equal to minus b. So minus b means it becomes 96. That is, ax square plus bx plus c equal to 0. So here a is already known to you. B is known to you, and C is, so therefore the root of this equation can be found it out as minus b plus minus b square minus 4ac divided by 12. So minus B, that is 96, plus under root B square, that is 96 square, minus 4 into this become plus 189 divided by 2 into 224. So if you calculate it and find out the value, you will be getting it under root 96 plus, you can solve it, 96 plus under root 96 square plus 4 into 224 into 189 equal to divided by 224. This is equal to, the value of D therefore comes out to be 1.157 meter. So the friends, you can solve and find out the unknown. This is the depth of embedment. So the first part of this problem is over with the answer. So depth of embedment D equal to 1.157 meter. So in a sheet pile, you can always find out the depth of embedment by drawing the pressure distribution diagram and calculating the depth of embedment. Now, if you want to find out the maximum moment, the locus of maximum moment is going to be like this. So the maximum moment locus, if you draw the locus of maximum moment across the height, is going to be like this. So the maximum moment will be in this part. Let's say at some distance Z1, the shear force is going to be 0. So wherever there is shear force is 0, that implies that the moment will be M max. So maximum bending moment. So we say that shear force is 0. It will be 0 within this. So that distance is Z1. So let Z1 is the distance from dredge line where shear force becomes 0. Therefore, find out the shear force. This is a cantilever sheet pile, and therefore already you know PA. PA is acting 30 minus this is acting this way. So you can find out, this is already known to you, 140 into Z1 is the force that will be acting this way, must be equal to 0. Therefore, Z1 equal to 3 divided by 14 meter. So 3 divided by 14, if you calculate, So 0.204 meter. So 214 meter from dredge line. So that's where at this location the moment will be maximum. So to calculate the maximum moment, let's find out the magnitude of the maximum moment. So 0.214. So now the second part of this problem is calculation of maximum moment. A max at this point, this is a cantilever, so will be equal to PA. So PA is already 30 kilonewton, and it is acting from the dredge line at 1 meter, plus Z1 you have already found out as 0.214. This force is going to act in an anti-clockwise manner, minus this force will be 140 multiplied by 0.214. This is the magnitude of the force, multiplied by the distance from this point where the shear force is 0. So it is going to be equal to Z1 by 2. So 0.214 by 2. So this is the magnitude. So if we calculate 30 multiplied by 1.214 minus 140 multiplied by 0.214 squared divided by 2, the value is 33.21. So 33.21 kilonewton meter. This is the magnitude. This is the answer of your part 2. So with this, we have solved this problem completely, and I hope you have understood both pressure distribution diagram, calculation of depth of embedment, and also calculation of maximum bending moment, etc., etc. So thanks a lot. Thank you.